And then what I want to do is I will introduce John Davis, our speaker. So first the official stuff, and then I'm going to say something else too. So John is a researcher in Microsoft Research's Silicon Valley lab, which he joined in 2007. He has widely varied research interests, which include computer architecture, large-scale systems to embedded systems, FPGA-based systems, application behavior and performance tuning, and hardware-software co-design and interaction. So John was previously a member of Stanford's Hydra Research Group, which investigated a thread-level speculative single-chip multiprocessor. And then John also spent 3 years working in Sun Microsystems' Niagara Architecture Performance Group. And John received his MSEE from Stanford with an emphasis on compilers and digital circuit design. And then in 2006, John was awarded a PhD, and his research focused on flexible architecture for simulation and testing, or FAST. And then secondly, I wanted to say that in January of 2010, when we kind of restarted this chapter activity, we put out the word to a number of people who were CS members in Silicon Valley that we needed a home and a place to meet. And this one lone voice spoke up, and it was John at Microsoft Research. And he worked with us and let us use their facility at Microsoft Research, which is where this group kind of got its rebirth in 2010. And I don't know how many times, John, we packed it out with 150 people and 130 people, and it could fit 100 seated. So those were, you know, exciting times. Now we're happy also to have Cadence with this auditorium that can fit almost 200. So with that introduction, I think we're ready, John, for you to, oops, get that mic popped on there. Okay. And we'll give it a test. He just had the mic just kind of pop off his shirt, so we're going to...
All right. Is that good? All right, excellent. Thank you very much, John. Thank you for having me. It's a pleasure to talk to you guys. Feel free to ask questions at any time. This is pretty easy, small group, so it should be fun to have some interaction. Today I'm talking about StarCap. It's a cluster power management system using software only, so there's no hardware to tell me how much power I'm consuming and what's going on. Again, this is work done at Microsoft Research in Silicon Valley, and my collaborators are Susie, Moises, Hasan, and Laura. All right. So I'm going to start with a summary of what I'm going to talk about, so it gives you an idea. If you go into some food coma land, you'll be able to at least know what we're going to go through. First, I'm going to talk about the power models behind this work, and this is kind of the foundation of the work. We call them composable, highly accurate OS-based power models, or chaos, and we're using these in MapReduce style or batch operating system type environments across a wide variety of clusters, and I'll go into the details of what clusters I'm using. And the clusters are small. There are 5 machines each. We have defined a new error metric to define how well those clusters are working. So we call it dynamic range error, or DRE, and I'll define that later as well. And really what we've gone through is a process to create an automatic framework for building these power models so that when new clusters come online or new applications come online, it's very easy and you can do it very rapidly to build power models. Now, with those power models, now we can do a bunch of interesting things. And for the information I'm going to present today is really looking at these reactive versus proactive power models. So reactive is just what you expect. I'm monitoring the power, and when I exceed a threshold, I try to do something to the machine to reduce the power. And this is, looking at how we can create the power models and have them be equivalent to power meters in the system. Now, once we have a power model, we can do some very interesting things. We can actually predict or try to predict the future, where the machine's going, and a priori prevent it from exceeding the power. So the proactive power models are doing that. And I'm just using standard DVFS, or dynamic voltage and frequency scaling. This is ubiquitous across all machines now, and so it's a nice, easy knob to do this work with. But if you had other knobs to tune, to play with, like hard drives or memory or those types of things, you could integrate that into the system. And then finally, what we've seen from the results is that you really need a proactive and reactive framework combined to handle all the characteristics of the two main applications that we have. All right, so that was a summary. I'm going to go into the background on power models. I'm going to kind of give you an idea of what are the difficulties in building these power models and building them for clusters. So most previous work has done work on looking at single machines and extrapolated those out, and we're actually going to apply them to multiple machines. And then with this automatic framework, I'm going to show how you can use it for the cluster power models and cluster power capping and go into conclusions in future work. And like I said before, if you have any questions or something's unclear, please don't hesitate to ask. All right, so why do we need power models? There's the academic purpose, right? No one really has done these large-scale power models before. We can see where things break down going from a single machine to these large clusters. We're also looking across a variety of platforms from the embedded space, say an Atom processor, all the way up to Xeon and Opteron processors. So we're trying to look at trends across the processors and families to see what's different. Now, you know, I work at Microsoft, so money is a big driver. We have lots of machines. And so if you can come up with ways to reduce the cost of the machines in a variety of different ways, then that's also good because that helps with the bottom line. Now, what does that mean? So in the data center context, really that gives me opportunities to both reduce the CapEx and the OpEx, the operating expenses and the capital expense. On the CapEx side, really what I'm reducing is the cost of the infrastructure or more efficiently using the power infrastructure. So there's two kind of knobs to turn there. I can reduce the cost of the computers, and for whatever megawatt target I have for the data center, I can actually get as close to that as possible without exceeding it. If you exceed it and blow breakers, people aren't happy, so you don't want to do that. So those are kind of the two things that I'm looking at. On the operating expense side, monitoring and building systems that actually can provide feedback about power is the other aspect. And so you can, you know, do it internally, build systems and softwares. You can pay people. I mean, there's, as you can imagine, some database backend, a collection of machines, and you dump the information there. So what we've done is integrated this into the overall system, which makes it easy to access and build. So in the data center context, why would you need it? Well, if you want to figure out which workloads can I run together in a series of racks or a colo, this helps you with that. You can do better capacity planning, as I mentioned before. For new systems, you can go through this whole process of building up models such that you can use them to predict what power will be used in new instances, and that's nice. There's also this interesting trade-off between system utilization and power. Machines aren't really power proportional yet, so you want to be able to deal with that, and a few other things. But in general, what we're seeing is if I want to add measurement infrastructure to my system, either at the server level, the rack level, or the colo level, that's, you know, a significant cost, millions of dollars to do that, and it changes what plugs you use in the rack and all these other things. So we can do some significant cost savings. And in general, we have some interesting aspects with, you know, respect to systems that are legacy or new systems, or dealing with error-prone issues like data collection or corruption. All right. So the goals of the power modeling are pretty straightforward. I want it to be online. I want it to give me the full system power. I have a variety of different model requirements that I'm just going to kind of walk through. It should be non-intrusive and low overhead, so I want to not perturb the system. So I don't want to use 5 or 10% of the CPU utilization to run my power model. That would be bad. It should be easy to develop, and there's a nice Microsoft Windows framework for that. There's also the same thing that applies in Linux, so this is kind of agnostic to the operating system, although there's different things you have to do. You have a question?
Yeah. You normally do DC separately, DC part separately, AC part separately for modeling, monitoring, control. That's one aspect of it.
Mm-hmm.
If you're covering the good. And what about cooling part of it separately from the main operating point?
So the questions are, what are we modeling, I think, at the high level, DC or AC? And then what about the cooling power?
You do separately what you're doing.
Right. So as you'll see in the next couple of slides, we're looking at what you would consider wall power to the machine. So if you plug the machine into the wall socket, what's the AC power coming out of that? And it's average, so it's not instantaneous. So there's some fudge there. In terms of cooling, we're looking at, there's two levels of cooling. There's the cooling that the actual system uses for fans and whatnot, and there's, in the data center context, the overall chillers, cracks, that kind of stuff. I'm not dealing with that at all.
Okay.
So I'm just looking at what the machine power is, and then there's a bunch of other things that you can do to model your efficiency on the cooling side and try to reduce the overhead for cooling. But that's a separate topic.
Yeah, control the fan.
Exactly, exactly.
What about high-end, like the water cooling, anything that's required in what you were saying at all?
So the question is about different types of cooling methods.
Yeah.
So
How can you modularize?
you can. This talk's not going to talk about modularizing cooling and data center design. That's a whole different talk, and I'm happy to talk about that afterwards. But we're really focused on, how do you go from a single machine power to racks of machines to hundreds of thousands of machines, and that's really the challenge. All right. So again, non-intrusive, easy to develop, and you want it to be fast enough for online use. So for those in the audience that do processor design, if I look at a power model based on circuit building blocks, modules, that's a very slow process. A lot of detail. You have to get the RC stuff. If you're even more hardcore, you're doing inductance. There's a whole bunch of things that you have to do, and you can't do that in real time, right? Whereas with this, we want to be able to run applications and vary the power of the system at real time. So that's one of the constraints we have. Now, this is just data that I collected. What we have here is two different power meters. The blue power monitor is the inside of the box. This is measured after the DC power supply, so you don't get any of the loss of the DC power supply, so that's why it's slightly lower. This is also measured at 5-minute intervals, so it's averaged over that 5-minute interval, and this is something that you can get for your Dell, HP, whatever box, right? You can buy this off the shelf. The administration of this system is different from the administration of the box, so if I want to change these granularities, that's difficult. In some cases, depending on how much I spend, if I'm on the cheap side, I might only get granularities to 30 seconds versus a second. Now, the red line is showing the variability of power at 1 second intervals. And so you can see the lag, and you can see if I try to make decisions on how to actually manage the system from a power perspective, if I use the external power meter, I can actually get some good reactivity. If I'm using the internal one, I'm kind of lost. Now, there are points that I've highlighted in this graph where the power has peaked too late, and so I might do something adverse to the machine, and so that's the issue there. So this is an instance of the hardware not being able to do what I want in terms of a sampling frequency. And with all systems and all services, you can pay more to get what you want. So this is just an example of the low end. All right. So measurement in general is pretty accurate, and so we want our system to be as accurate as possible. We're targeting 10% using this dynamic range error, and when I define it, it'll become more clear what that means in terms of the 10% number. But we're really focused on the dynamic range of the system from idle to the maximum. And this new metric is much better than what people in academia have previously used. And then I want to be inexpensive. If I look at my HP server, the list price for power management is a couple $100 per server to implement and to buy. And so I want to reduce that overall cost. I don't need to have additional hardware and software in my rack or colo. And in general, if I look at the Facebook design for the Open Compute, that actually has no ability to monitor individual server components. They just didn't want it in. They didn't want to pay for the extra cost. So this is something where you could apply on a low-cost server design.
Is this application independent?
We're going to get to that. That's one of the tricky parts. So yeah, so there's some interesting information about how we train these models and how we're trying to make them application agnostic. Yes, John? Oh, sorry. So the question was, are these application-specific models? And we're trying to move to application agnostic. There's a lot of work that you need to do, but I'm actually going to use 4 different applications, and you'll show how this actually works. All right. So, and then finally, we want it to be scalable and generic. So scalability, we want to do this 100,000, million servers, that kind of order of things in the data center. And we get a generic portable infrastructure by using the OS level performance counters. For those who have done performance counters on processors, you know how painful that is. Each processor, each family has a different set of performance counters across different vendors, whether it's AMD, Intel, whoever, they're different. I mean, it's painful. So you don't get portability that way, and we're trying to use the OS to bias that. Now, we are giving up fidelity, right? So there's some interesting trade-offs there as well. All right. So kind of a high level, what is a power model? There's some inputs, there's some type of function, and we get power out. Previous work has been in simulation or machine learning functions, and it's really been focused at the component level. So how much does my floating point unit, my processor, use for power? How much does my overall CPU use? And we can use a variety of different states, information. So current state, architectural parameters, circuit level parameters, design information, hardware counts. Those can all be used to get these component level information. And depending on where you are, I can be anywhere from high fidelity down to low fidelity. It's just a matter of what I'm trying to achieve. Most of this, as I said, was processor focused. So there's a bunch of papers from IBM, some from Intel that actually go into this, a bunch of academic papers from Princeton and some other places. So the problem overall with these are they're generally not real time. So I can't get at the millisecond or nanosecond or even second granularity power numbers for a processor, for instance, that are high fidelity. And of course, if I look at a power architecture versus an Intel x86 architecture, there's no portability across those. They're completely different. They're different technologies, and so that's one of the issues that we have, why we can't do it in the old ways. And we don't really want that kind of detail. Now, what we're doing to try and achieve this is we're saying, okay, across the system, the OS is basically the resource manager. It knows what's being used when. And so if we can use a unified structure like these OS level performance counters, we can apply these as a function and then get full system power out. So I can get CPU activity, I can get memory bandwidth, I can get disk activity. All the components that make up the full system, I'm going to combine those using machine learning to get an actual system power out. And it's going to do it on an application and aggregate application level. And so really what we're doing is we're building a framework. We're trying to figure out which features we need, a bunch of different things there. From an accuracy standpoint, is there variability between machines to machines? What's the trade-off between the type of model, parameters, versus the complexity and accuracy? And again, you want to be able to scale. So that question really is asking, how many machines do I actually need to sample to build these models and build a good model? So depending on time, I'll go into some details on the sampling side. All right. So really there's these three ABC different ways of doing power modeling. The first one is basically the first approach, where I took one machine, I created a model for it, I say that everyone else is identical to that machine, I just multiply by n. I have 5 machines, I have one model, I just multiply by 5. That gives me the power. This has limitations. Not all the machines do the same thing at the same time, and as I'll show later, there is variability you have to deal with. Now the other way that we can do is kind of this intermediate step, which is I'm going to model cluster power by taking an aggregate of some number of machines and creating a machine model that approximates that collection, and then using features from each machine to then give me the power. And this gets us kind of halfway in the middle of the spectrum. And the final one is, given n machines, I'll create n models, and I'll take inputs from each model, and I'll create very accurate cluster model for the power. Now the problem with that is if I have 100,000 machines, I need 100,000 models. You can see how this becomes intractable very quickly. Yes? So the question is, using my techniques, will it affect the performance? So what I'm going to show is that I'm not going to. And I'm not going to affect the performance. It all depends. There's a lot of different knobs here, and it depends on the granularity of sampling and some other things. But most of the model building that I'm going to describe is done offline, and then you apply the actual model at runtime. So we'll see that. It's going to be, so the question is, do my models affect the performance of the system? Right. I'll get to it, but it's 1% CPU utilization is the overhead. Yes?
In a big data world where massively have many virtual machine clusters are turned on and turned off, it all depends on the application, who is using and so on. How responsive, this kind of models would be, number one.
Yes.
And if it's the other extreme where it is a video game or video on demand, that kind of application, where it's continuous streaming for a given minimum amount of time, and these models don't really cut it.
Oh, you'll see. So the question is, how do my models work, and how do they react, and how fast?
It works in all cases.
I'm going to show you data, right? And that's the good part about this talk. But once we build the model, so let's build the models first. So in the feature, so right now what I'm going to talk about is the cluster power model challenges. What are the things that make this difficult? So from the model feature selection process, if I look at event trace for Windows performance counters, there's over 10,000 of them. Which ones do I use for building the models? As I'll show, machine power variability is an issue. I can't just say this machine, this SKU of a machine. So I buy 10,000 Dell X boxes, whatever that box X is, and I can't assume that they're all going to use the same power when they do the exact same thing. So that's an interesting challenge. So to bring that point home, basically what I have is 3 different machines. I have 2 sets of numbers. On the right, I'm running a CPU intensive benchmark. And I basically ran the same thing and rotated the 5 meters across that. And I have a 10% variation from high to low. Across meters, they're pretty close. But across machines, there's a 10% variation. So that's an interesting thing. And it exists both at the high end and at the idle time. So things like slightly different versions of DRAM or various SKUs of the processor, they're all binned and there's a distribution. And that distribution plays out into different power of different machines. So I have to deal with this variability in my system. Of course, the number of machines, how many do I need to model? That's an issue. Within the data center, I don't have the same machine. I buy machines in large quantities over time, and so there's different types and sizes of clusters. They're homogeneous at large numbers, 10,000, whatever, but there's multiple groups of those, and so that's something to deal with. And so when we look at this infrastructure, what I try to do is capture the wide swath of x86 processors that are available. So moving from left to right, I have the Atom embedded processor, which is a pretty straightforward, simple processor. It's low power, low dynamic range. I go into a high-end mobile processor, the Intel Core 2 Duo, which is a little bit old, but it gives us a lot of dynamic range and is really a target for where efficient computing, I think, will go. The Athlon is a low-power desktop processor, and then we also have 3 different systems with server, either AMD low-power Opteron or Xeon. And so you can see the range is dynamic power from 4 watts all the way up to 110. And we're going to try to model those with different models, but across all the different systems. And just so you have an idea of what the setup is, I have a rack switch that's connecting these 5 machines together, and I'm running these batch jobs across those 5. And then in terms of the actual measurements, I'm measuring all the systems with this off-the-shelf power meter, and that gives me 1 second granularity measurements on the system on test, and I record it there. All right. Give you an idea of the software infrastructure. I'm running 4 different applications in this MapReduce style workload, and they have different characteristics. Primes looks at the prime numbers, a million different prime numbers, and that's very CPU intensive because it's using a floating point operation. The PageRank is network intense PageRank as for search. Sort is disk and network intensive, and word count basically just reads stuff off the disk, counts the occurrences of words, and comes up. And so in the Microsoft parlance, Dry and Dry Link are the MapReduce style frameworks. Artemis helps me collect the data. It's a logging system. The ETW, Event Trace for Windows, is this collection in infrastructure for collecting these features or performance counters. Joule Meter provides this metering process for using the power meter and injecting that stream of data about power into the ETW framework, and R is a stat package that we use for doing the machine learning stuff. So that kind of gives you a sense. Now, at a high level, I have 4 different applications, and they have completely different power characteristics. As you would expect, since Prime is CPU intensive, it has this nice kind of plateau, whereas PageRank has a lot more variation. So this is what I'm trying to capture in the models. And ideally, I'd like to have one model capture all of this behavior. So that's the challenge that I'm going through. All right. So I'm trying to build these models. How do I quantify if those models are doing well? So for the Atom box, I have 4 watts of dynamic range. I have 22 watts of static power. So if I compare the overall system power to just that dynamic range, I'd lose a lot of information. I would unfairly bias a model to saying it's good when it's actually not doing a very good job. And that's really what mean squared error or average or median error are doing. They're taking the overall system power and saying, how close am I, and not removing that bias. So what dynamic range error does is we say, okay, what we really want to look at is the area where the actual activity happens and get rid of that bias. And the model is really telling me how well do I model that variation within that range. And so what we take is the mean squared error, the square root of that, which is basically power in our case, and divide it by the range. And so that tells us how good we are. So if we did this with the Atom box, right, it's only 4 watts. That's the range that it's operating in for the single system. Whereas if I look at the overall power, that would be 26 watts. And so you can see how that can bias your answer. So this is a little bit more stringent. Now, as systems become more power proportional, so if the CPU is running at 0%, I'm close to 0% power. If I'm running 100%, I'm close to 100% power. If you get that nice linear curve there, then this degrades to mean squared error or average or median error. So as we improve the systems, these kind of converge. All right. So you might be tempted to say, well, machine learning is this great tool. I'm just going to let it go and do its thing. And that's not the right approach. If you think about it, I have 5 machines. I have 10,000 metrics per machine. The machines are doing some coordinated workloads, so there is some correlation between the machines. And so there's really no good way to combine all the features, push a button, and then voila, come out with a good model. What you'll get is it will be application specific, it will be run specific. There's all these things that allow you to generate useless models. And so I would just caution you about relying on tools that may do some good things, but there's parameters and constraints that you have to be aware of to actually make it useful. And so, in this case, you can see that I could create, I run primes and I get a model for primes, and that's for that one instance of running it because of the way the configuration was, and you want to stay away from that. All right. So really, kind of the first thing to do is, deal with this model feature selection. So from an architecture standpoint, when I look at a system, there are certain things that contribute to the power. And so a lot of these higher level .NET or application performance counters I don't need. So I can whittle this 10,000 features down to, in this case, we'll get 10 per model approximately. But I can remove about 9,000 of them. I can get down to about 250 if I just say I want processor, I want network, memory, all the different components from the physical space that make these up. And then from there, there's an issue of removing features that aren't independent. So what we've done, as I mentioned, is that architectural selection process gets us down to 250, and those are the areas that we grab them from processors to, there's a few set of application-specific ones. And then what we do is we say, okay, this is kind of overkill. I have 10 processor performance counters. Which one do I actually need? So what we do is we create a correlation matrix, and we remove ones that are highly correlated. And this is above 0.95. And we did a sensitivity study, and this is kind of where it kind of was a sweet spot in terms of doing that correlation. And that only does part of the process. That gets us down to, as I mentioned, 45. And then we do this linear regression process where we say, okay, I have a collection of features. Which ones can I remove, based on the performance counter definition. So in MSDN, they actually define what the performance counters are. And so you can actually read through and say, okay, I can catch the A is proportional to B, but I can't always catch the A plus B equals C. So one of those examples would be user time versus kernel time equals total time. So there's some interesting caveats there that they don't always work out from a correlation matrix side, but you understand from the definition how to remove that. And so once I do that, I get to 45, and then by applying linear regression, which is a very straightforward process, I can come up with a systematic way to get down to these 10 most significant features for that application, for that cluster, for a collection of workloads, and that's really what I'm pushing for, and that's kind of the hard part. All right. So I apologize because this might be hard for you to read, but of the 6 machines, or 6 clusters with 5 machines and 4 workloads, this is the collection of counters from network, memory, physical disk, processor, microprocessor, microprocessor, file system cache, job objects, which is really memory, another memory one, and performance, processor performance or megahertz. Yes?
Slides back, you had showed graph comparing the amount of power consumed for any given solved activity, for example, running the Bayesian calculation.
Sure.
My question is that across systems, did you see that when a system runs a particular kind of activity, is the performance counter the same? For example, if 2 systems are running the Bayesian algorithm, do they both show the same value for the performance counter? And does it then translate to different power levels because of system-to-system variation? Or are they different right from the start in terms of performance counter values?
So the question really is related to, are the performance counters unified across systems and have the same type of behavior regardless of system, but specific to an application? Correct? Fundamentally, you'd have to go back and figure out and correlate the phases of the applications to the systems. And what I mean by that is the systems I'm presenting are widely different in terms of the frequency. So I have the Atom at 1.6 gigahertz, and I have, I think the Athlon's the fastest at 3-something, 3.2 gigahertz. So,
Like, offer the same kind of processor, but I know you have just one of each.
oh, well, I have 5 of each, and so those are doing the same thing. So if those are doing the same thing, the performance counters are very similar. So this is why when I apply machine learning, if I have this, if I take a application like primes, it has a variety of different phases of the application, and they operate in lockstep. There's like barriers between each different function. You can do some mapper, then the reduction process that between the mapper and the reduction, there's kind of a barrier to get everyone to finish so that I could do the next step. So within that, because I partition my workload across multiple machines, they're all pretty much doing the same thing. And so what happens on the machine learning side is it will say, wow, these 3 machines are doing the same thing from a performance counter perspective. I just need one.
They're treated as commodity processors.
They are commodity processors, but the issue is that I can aggregate the performance counter into one, and so now I have one collection of 3 processors that are doing that thing. If I change that and I rerun the same application, then I'll get a completely different number because now there's a different set of 3, and maybe that processor that is the one that's saying I'm the guy that tells you how these 3 work is not in that group. Right? So within the same type of system, yes. But I'm trying to remove that so I can apply these models across the whole cluster. And that's really what drives us to that B level where I have a machine model that then I bring in inputs from all the machines and get the power from that perspective. Is that clear? Okay, excellent. All right. So these are the areas. And what we're doing here is we're saying, okay, I apply these linear regressions to the system. I have power as my what I'm trying to predict, and I have a bunch of features. And what this is showing, and I have on the bottom basically a performance counter number, but really it's the categories from left to right, network, processor frequency, all that kind of stuff that I showed before. And what I'm showing is, does linear regression tell me for those 5 machines if that feature is significant? So a bar of 5 means that all 5 machines, the models that I build for each one, is saying that that's significant. And so for CPU utilization, which is 102, right? Remember these numbers, that one is significant. For frequency, that's also a significant indicator for power. Whereas on the other ones, they're not all significant. So even across the same machines, doing the same type of workload, I get variability in terms of which features to select. So I have to come up with a method to deal with that. If I push it one step further, right, so these different machines, same workload, exactly the question that was asked, right? This is a very interesting problem to deal with. And so how do I narrow the scope and actually pick which features are significant? Now again, when I do this across all 4 applications, in this case, 20 is the high point. That would say that all 5 machines across all 4 applications said that that was a significant feature. Again, we see it's not 20, but there is some level across these 4 benchmarks which allows me to get there. Now, we came up with a heuristic that says, okay, well, how do we actually now select the features so that we can make a model that's applicable across multiple applications, as per the question earlier. I'd like to have a single model that's good for all the applications. I'm going to give up some accuracy, but I'm going to trade that for simplicity. Right? So what I'm going to do is I'm going to create this box of model. I'm going to create a threshold at some level. In this case, I started at 7. And I'm going to pick all the points, all the features that are above that, and I'm going to put it in this model. And I'm going to run linear regression again. So now I'm going to cross all these machines. I'm just going to create a subset of those features. And then those are going to drive whether the model is good. And when I build these models across each machine and each feature, I'll get a set that are significant and a set that are insignificant. And what that does in this diagram is that moves the line either up or down. If I have insignificant features, it's going to move it up. If I have significant features, it's going to move it down. And so that's one way you can build the heuristic to actually build these models and do the feature selection. And you hope you only have to do that once for this collection. And so for this case, I think we started at 5, and using the stepwise regression process, that blue line is 7 is the feature that actually ended up for this particular cluster, the Opteron cluster, for that collection of workloads. Now, in general, if you were to recall the numbers of the features, these are the different models, and they're quite different. Opteron has some, the Intel boxes have a lot more features because there's a lot more hard drives in the system, so they're more sensitive to that. And if you think about this, I've now done this at a cluster level, right? And I said, okay, each cluster now I can do the stepwise regression. Why not take the bag of all the features across all the different clusters and do the same thing? And that's what this general model is. I'm giving up, again, some accuracy, in this case 1%, but now I can pick a cluster of features where I don't have to do that across all systems. And for this particular case, the first 3 clusters that we picked, we threw that in a bag, and that was the majority of the features. We didn't actually get more features as we added beyond the 3 clusters. Yes?
Just the example of 1 or 2 that you shared.
Mm-hmm.
Some of them dominate in the FR that we have versus the other. Some of them are so big,
Mm-hmm.
the others are so small, that adding all of that doesn't even count to that. Is it not sometimes practical to pick only those which are dominant and just count the number of little jets?
So the question is related to features that may dominate other features. And this is a problem that we solve pretty straightforward by normalizing the inputs. So what you really want in the end of this model is something where the coefficients of the model are relatively the same, and the weights of the model, of each feature in the model, are relatively the same. And you do that through normalization. So we had, mean at 0, distribution of 1, and that was the normalization factor.
But using the same logic, is there not any dichotomous decision making you have to do in terms of processor performance optimization versus processor power performance optimization, right? You are doing separately from processor how well it does, how well the utilization versus the power optimization. What you are focused is your performance power performance sensor, rather than how well it does, which resources it uses, and so on. Which drives it? You see the contradictive, sometimes contradictive, not always.
Right. So the question is really, am I trying to create a really good power model, or am I trying to create?
Processing model.
Right.
How it does the thing.
Yeah. So.
It's a matter of cost, ultimately.
Right. And we'll go through some of the cost functions for this, but at the high level, what you'd like to be able to do is tie these features back to the actual individual components, and then use those to throttle those components. So if I had a power cap at some level, which was small or big, that would determine which knob to turn. And what we're doing, we're just using the processor because that's the most ubiquitous power management knob. Yes? So the question really is, which was the most efficient architecture? So this talk won't cover that, but in this set of workloads, the Intel Core 2 Duo, the high-end laptop processor, gave us the best efficiency across most of the applications. So, but that's a different paper, different topic. But that answers your question. All right, so let's go back to this power variability that I was talking about. And again, what we see is this 10% delta, both at idle and full CPU utilization. So we need to be able to model this, and I just wanted to recap on that and how do we actually deal with that. And what this is showing is that, the power models that I'm using, or the power meters that I'm using, have plus or minus 1.5% error. And so one of the things you could ask yourself is, well, the error of the monitoring, the power meter that I'm using basically obscures the variability that I actually would measure. And so you want to understand if that's the case. Now, in the Opteron case, the deltas that you'd get from looking at this 3% span is greater than the deltas that we actually measure. So in some cases, you could use that. But what I'm showing here is at idle, For the Intel and the Atom case, that's not the case, right? I have a distribution on idle power that's much greater than the error in the meter, so that won't work. And then depending on the application, I get variability there too. So I can't use the error meter of the meter, and that changes from meter to meter. I can't use idle. I can't use the application. How do I actually tell how many machines I need to sample to create a good distribution to capture this variability? And so that's the next thing. And so when I'm building the model, there's a couple different approaches I can take. Now, if we go back to that first case where I say I'm going to take one machine, build a single model for it, and then see how good that is. That's basically this case right here. On the x-axis, I have the number of machines used and which machine were used to build the model, so node 1, node 2 through node 5. And each color is a different application I'm building it for. So if I use that one particular machine, in this case, this is the Atom, which is the smallest one, I can get really bad error. I can get 150% DRE. So that's not the process that we want to do. If I do B, my error is node dependent, and so that makes it difficult as well. So, and again, you know, if I go all the way out to C, where I say each machine will have its own model, then I remove the luck from the selection process, because there's some that actually work very well. Node 4 was a good proxy for the other 5. Node 5 was a good proxy for the other 5. But what you'll see from the trend is I add more and more machines to the mix, I actually reduce the error, and so I'm getting that aggregate that I want to get. So this is what's driving this process. So I can achieve, you know, the ease of this cluster model B and the accuracy of C if I increase the number of machines that I sample. So then the big question is how many to sample. You don't want to have to sample 100,000 machines to build a model, for instance, if you have 100,000 machines. So there's this Chernoff-Hofting bound. It's a very nice bound in the sense that it gives us a very small number of machines that we need to model. If we have a sense for what the span is or the spread is on the power, then that will tell us how many machines we have. And by putting this in an equation and saying that we want, say, 85% of the machines to fall within that sample group, then I get on the order of 20 or less machines that I need to sample out of whatever population. It's population dependent. So that's a very nice characteristic. And really, this is not the correct way to describe it, but this Chernoff-Hofting bound is talking about a span. And it's not a Gaussian distribution. The worst case is machines on either end of that. And so that's what we are actually predicting the sample size for. If it was a Gaussian distribution, it'd be much easier to deal with. And so I think this is a little bit conservative. So this really allows us to use that technique B, where I create an aggregate model using a collection of machines. So there's a single machine model, and I input the specific inputs from the machine to actually get to the endpoint there. So that's a nice outcome. And so what we ended up doing was that kind of covers the feature selection. Now there's multiple modeling techniques that we can use. We can use a very simple linear model. AX plus B equals the power. We can use a piecewise linear model where we slice and dice the space up and combine them that way. We looked at quadratic models where you have interactions between the different features, and a switching model where we basically partition the space. And so what's happening here, if I look from a modeling standpoint, from top to bottom, my models are becoming more complex with respect to the feature space. So at the top, it's one feature for each one, and it's very straightforward. It's a one-to-one mapping. At the bottom, you could think of this as in the dynamic voltage and frequency space. If I took each allowable frequency, I would take all those features from that frequency and build a model for it, say 1 gigahertz. And then I take the same collection of frequencies and build a separate model for the next level, which is maybe 1,500 megahertz, right, and go from there. So that's kind of what I'm talking about in terms of flexibility. And this adds to the complexity and compute overhead of the system. So ideally, we'd like the simplest model that gives us the highest accuracy. Right. So we built a variety of models, in this case 16 per cluster. We looked at the trade-offs of feature and model complexity, number of features, and those types of things. We also included history. So does previous frequency of the processor give you an insight into what the next state might be? And in general, we use that general feature set that I described, when you take all of the features across all the clusters. And that really degraded performance by, accuracy by about 1%. So it's pretty close. That's pretty good. And the goal there would be then to remove feature selection entirely. You still need to do more work, but that would be the end goal. That would be ideal. So I'm going to show two graphs. This happens to be for the Opteron. There are basically two classes of applications with respect to the features and the models. There are, what we're seeing on the left are basically the modeling type is the most important. So what I'm doing from left to right is showing the type of model, so starting with linear, and then what features you need in that model. So just using the CPU utilization is the simplest model, moving over to the cluster-specific models that we had before. So you can see there's not much delta there, 8 to 14%. But once I get into a piecewise linear or quadratic or other types of models, those more complicated models, they actually are able to model system power much more effectively, and features aren't that important. All right, so that's an interesting half of the applications, 2 of the applications fit in this space, and in this case, the other 2 fit in the other space where it's not the modeling technique, but the features that you're using. And so the combination of using a good model, so quadratic or switching or something like that, plus a more explicit, larger feature set gives me the best of both worlds, and I can cover both of them that way. So that gives you kind of the 2 spaces that these models fall into. So that's kind of the overall modeling. And just to kind of wrap up, I'm getting portability because I'm using these OS level counters. And I did this in Windows, but you can do it in Linux because there's similar counters there. I'm getting high fidelity. I'm using these multiple machines, and I'm quantifying the number of machines to build these models. And I can account for variability by basically aggregating machines together, and that sample size tells me how many to do that to actually build the model. And we've got good feature selection, and there's good correlation between the measured models and the features that we're using. In general, we're doing standard stat techniques, doing 5- and 10-fold cross-validation. The test sets are different from the train sets, and the test and train are different by order of magnitude. And really what makes this tractable is that sampling theory. I can do on the order of 20 machines to cover hundreds of thousands, right? That's a nice thing, and it's independent of the population size. So if I know the span, or I have some idea of how the span of machines are converging, then I can make a good estimate of how many I need. And what those previous graphs showed was that, the DRE is 10% or less. So now how do we use those models? And that's kind of the other interesting aspect that gets into this power management aspect. So let's go into cluster power capping. In general, a power cap is a soft cap. There is some type of limit that you set for your machines, and there is a time bound of how long you could exceed that. The low-end systems do 30 seconds. The high-end systems do half a milliseconds or less. And so there's some interesting variations and obviously cost associated with that. For our system, we'd like it to be flexible and low overhead. So these low overhead power models obviously fit into that. They're using less than 1% of the CPU utilization, so we can actually use them and not perturb the actual underlying system. Most of the cheaper systems are using measured power and then reacting to that measured power. So we're going to use that as our baseline in terms of the comparison, and we'd like to show that the measured power is the models are as good as the measured power in terms of the reactive system. We're going to use the same control theoretic type. Actually, it's more of an ad hoc system to do the reaction, but we're either using measured or the model. And then finally, because we have this model, we can actually predict in the future where we think the processor is going. So we use that to determine if I were to change the dynamic voltage and frequency state, would my power exceed the power cap? If it does, I don't let the system do that. If it doesn't, I allow the system to do that. And then finally, once we have this system, what we can use it for is uniform and non-uniform power capping. So if I look at my application, different processors might be doing different things, or different systems might be composed to do different things in a rack. And so I can actually allocate power to those systems however I want. And so that's a nice aspect, whereas some of the other systems, it's a uniform, it's kind of a peanut butter. I have 200 watts that I give to all the machines, and they can't exceed that. And so that can be limited from a performance perspective. All right. So what we do is we build a 2-level system. There's a top-level power management policy system, and that just says, am I doing uniform? Am I doing non-uniform? How much power do I allocate to each system? And it really sets up those power caps. And the second part is actually within the system itself. So there's the power model itself and then the power control. And this allows me to separate the mechanism from the policy. So I can deploy a policy at the high level, and then the mechanism can be determined by the actual server. And when I want to deploy new mechanisms, it's very easy to do. I don't have to worry about changing the policy process here. In this case, because power management's not as ubiquitous as you want, the one knob that we have across all systems is dynamic voltage and frequency scaling. So I can reduce the power of the system by reducing its voltage and its commensurate frequency. And each system that we use has different, usually about 4 points from the low end to the high end. And as I mentioned before, when we talk about these power models, if I know what the target is, I might choose a particular knob to get to that power target. So if I had a hard drive velocity knob, I can take my 15,000 RPM drive and bring it down to 10,000 or 5,000, and that was something that I had in my model. I could equate the two and then use it that way, for instance, and that's outside of the processor. And again, what we have with this power model is I can report the ETW in the ETW framework, the power of the system, and so then that can be used by anything. There's a Windows management infrastructure which allows you to get that data from anywhere in your data center or your facility, so that's a nice thing. Nice side benefit. So what we're using in this example, as I mentioned before, the Core 2 Duo was the most energy efficient, so that's what we're using. Looking at power and processor and fine-grained control, this is really what we're looking at. If you look at multiple cores, many-core systems, actually being able to control individual power islands or individual cores is kind of synonymous to what the power budget of these current Core 2s are. And we're going to do this reactive and proactive. So reactive is this recap. I'm going to either use measured power, so I'm going to have mrecap is using the power meter to tell me when I've exceeded the budget. I have a linear model that I'll show probably later, and then the cluster-specific, or C-recap, is using those cluster-specific models that we had. I'm not going to show any of the general models. They did pretty much as well, so it's not really much to say there. Now, from empirical data, what we found is for the reactive case, the window of sampling, in order to make sure the system was stable so it didn't oscillate a lot, had to be about 10 samples or 10 seconds. And so that, if you're a control theory person, there's a lot more stuff that you can do with guarantees and all that stuff, but I'm not, so we just did empirical stuff. For the proactive predictive power capping, or ProCap, we use the cluster-specific models because we saw that to be good with the quadratic power model. And again, the general feature set is very similar. So we'll see the differences there. Now, what I am showing here is the individual Core 2 power for that server at different frequency caps. So on the left side, I have no frequency cap, and really what I'm showing is a batch jobs of word, count, prime, sort, and page rank going from left to right. Next power frequency, or next frequency cap is at 94, 82, and 70%. And this takes several hours to run these benchmarks. And the actual frequencies are shown at the bottom. Now, what I'd like to be able to do is set a power cap at 38 watts. So I don't want any of the machines in the cluster to exceed that as a nice fine-grained target. And then I'd also like to set one at 42 watts, which is below what we need. Now, looking at this information, really I either have to use, even if I pick 82% as the frequency cap, at 42 watts, I could get very close to that. So I could do this statically if I knew about the application behavior, but that would restrict the performance and I wouldn't be able to run as fast as if I had this dynamic control. At 38 watts, I'm forced to run at 70% to make sure I'm within that bound. And that is pretty restrictive. So what I'm showing here is the 38 watt server power cap. And what I've done is that black line is at 38 watts. And this is using measured power. That blue line is the measured power when I try to apply this 38 watt power cap to the system. And because it's reactive, what ends up happening is I exceed the power cap and then I correct for it. And the important thing to note are how high is that peak, right? And this is kind of the oracle. This is, from a measured standpoint, I know exactly what the power is. The other thing I want to note is how wide is that peak, right? Because that tells me how long the violation is. And so this is with measured power. Now, as I move forward, I've overlaid the cluster power model results, and you see, on average, is about the same. The peaks are about the same height, and the durations of those peaks are about the same height. So that's showing us that the cluster power model can be used to replace, in this instance, for all these benchmarks, the actual measured power, and I can get rid of the power meter, which is a nice result. Now, it might be a little bit, you can see it pretty good. So what I've now done is overlaid the ProCap policies on this. So I'm using the cluster-specific quadratic model, and I'm predicting a priori if the next cycle is going to tell me if I'm going to violate the power cap. And so what you'll notice is in general, the peaks are lower and they're much narrower. So I can actually, in a 1 second granularity, change, make a decision, and stay at that value and persist until it resolves. And so that gives you much better characteristics. Now, one of the things to note, even though it's not shown on this for this particular machine, there's a lot of variability in the static, in the page rank case. And so that is a scenario where my current state of the processor or the system in general is not a good predictor of the next future state. And so I get actually more violations there, even though it's not shown on this graph. So there are word count, primes, are good examples of cases where the current state is a good predictor of the next state, whereas static rank is not. And so this would allow you to then use two things, this proactive case plus a violation window, or reactive window. To that combination would cover both application scenarios. All right. Now, if we zoom in a bit, you can really see the differences in terms of how wide the peaks are and how tall they are. And so, again, this blue case here is the measured, the red is the cluster, and the gray, I can change the colors, that's the proactive. And the one thing to note is there are some oscillations, so I didn't do perfect control theory there, but it was, I'm not a good control theory guy, so you'll have to forgive me. All right, so that's just kind of zooming in to see the differences and what's going on. All right, now if we go to the 42 watt cap, again, this is the red dotted line. What you'll notice when I'm using the measured power, or even when I use this cluster model, I get these oscillations because I'm reacting to where the system is, and there's some hysteresis there that I haven't quite gotten rid of. It's not quite long enough. So I try to go up and approach the line, and then I get to a threshold, and I come back down. So I'm really oscillating between two frequencies to get there. If I use the middle graph as a linear, you'd never do this, but in previous literature, there were people that said I could approximate system power just using a linear CPU utilization model. And really that just takes the power all the way down to the bare minimum because CPU utilization doesn't capture the frequency information that we're using. So as you'd expect, that's not very good. And with the ProCap case, you can see that even though there's a lot of oscillations, I'm much closer to this line, I'm much more steady, and that's really what we like to do. We want to approach that power cap and get as close as possible. So then that gives us better utilization of my power infrastructure. And so that's kind of what this is demonstrating. All right. One of the other things we can do is we can actually do non-uniform power capping. So within these 5 machines, I can allocate different powers to different machines. And so what I have in this table is when I apply no power cap, the normalized performance. So closer to 1 or below 1 is better. When I go over 1, that means I'm actually running slower. And so in the lowest frequency state, this is that 70% point, I run anywhere from 16 to 42% slower than when I allow it to run at full speed. If I do uniform power capping at 190, which is about 15% less, then what I end up getting is about the same. And I'm just spreading the power cap across all the machines without regard to what they're doing. And in this case, if I do non-uniform power capping, I can actually give more power to one system, and it can deal with the critical path and actually finish faster. So I can regain 8 to 41% of the performance by using this technique. And so if you do it at a larger scale, this might mean that I can run more systems in my data center. I can maintain performance SLA guarantees, those types of things. So that's a nice outcome. And so, in general, what I've shown is, 2-level system that provides flexibility. Servers can determine their own power cap management process. It's easy to add new management techniques. The upper-level policy doesn't need to know about the mechanism, so that's nice. For this work, we were doing 4 quadratic models, 1 linear model, collecting all the data and reporting it, and that was less than 2% CPU utilization on the data that we showed for the Core 2. And so that demonstrates that even if we were doing just 1 model and doing reporting, we would much less, and so we wouldn't really impact the performance as per an earlier question. And to cover all bases, both applications that are a good predictor of the future and applications which has much more frequency and variability, I can combine the ProCap plus a history window to get me the types of power capping characteristics that I want. So that's a nice outcome. All right. So in conclusion, I've taken you through CHAOS, which is this composable, highly accurate OS-level power modeling. We've looked at how we can remove feature selection from the process by doing this general feature set, and this is just stepwise regression on a collection of features. As I add new knobs to the system, the models might require more advanced, I can do independent DVFS or core parking and add that to the power management mix. So that's a nice thing. And this is really, these models are providing us that nice way of reducing cost and replacing something that we could use to improve efficiency in the data center. And we're really looking at these energy-specific counters and associating those with the knobs as they become available. And again, I mentioned in terms of software power capping, you can do both proactive and history window, and this non-uniform capping allows us to improve performance without changing the power cap value. So what we can do in the end is reduce both the CapEx and the OpEx cost in the data center, which people like. Right? Saving money is a good thing. With that, I will open to additional questions.
Tell you what, before we do the questions, I just want to say thanks to John, and we'll do the question Q&A. So give me one moment here. One moment.
I'll get you, don't worry.
Kevin here. I want to present John with the certificate of appreciation. So,
thank you.
So thank you, John, for presenting this. This is all new territory for me, and we'll open it for about 10 minutes of Q&A then.
Sounds great. I'll let Microsoft.
After that, yeah.
I'll let the microphone. Go ahead.
Okay. Have you tried this in a public cloud environment? I know this is more of a private cloud you were talking about indirectly. Have you tried your model in a public cloud?
So,
Users are all not same,
right. I mean, you're really talking about how much coverage do you get on the applications, right? That's really the overall underlying question. Do the features and the coefficients for those features capture every application?
None of that is scheduled in a public cloud.
I can't say with a straight face that that's the case, right? I mean, the whole point of making the automatic framework was such that if you were in doubt about how good the model was, you could easily rerun it and collect data and then spit out a new model. So that's the whole point. You can contrive an application and then application plus plus. They're going to be completely different, and my models won't be able to capture that. So really, in the public cloud sense, if I know what applications people are running, like web services or something like that, then I can do that. And what ends up happening is I can, in the billing process, I can actually bill you for the power that you use, which is an interesting billing metric. Or internal customers, I can bill you for the power that they use. So that's one application of why you might use the power models. But going back to, I can't cover all applications with a single model. You can create something that breaks it. So we make it automatic. Yes?
Yeah, the DC power that is used is pretty high. Has it been related to the company, like Intel, whatever, that this is high, and any tracing has been done within the chip just to see where the DC power is going, or other units probably could be turned off? This is a little bit, it's outside your, so basically at the chip level, have you had any kind of discussions with the vendors that, what's going on there?
So, I mean, the interesting thing that we have seen over the evolution of these computers is it used to be the case that the processor was the thing that was a majority power-consuming device. And so all the models were CPU-centric. A lot of the power in the dynamic range is associated with the processor still. So when we get into these scenarios, it's still going to be processor-centric. But what we're seeing with the advent of more memory per system, more disks per system, not necessarily SSDs, but hard drives, you see equivalent power being associated with different things. And so you could imagine doing power management on the CPU as well as the memory, as well as the persistent storage, hard drives or SSDs or whatever. So what I have seen over the last 10 years is that the processor is becoming less and less the dominant factor in the server, whatever that is. And so that you're seeing these other features pop up as being significant. In this data, because the Intel boxes had more hard drives, between 4 and 6, that was a more significant feature than the other systems that only had one hard drive or one SSD, for instance. And so you can see that dramatically in the actual models that we built. From an efficiency standpoint, a socket in a server is basically relegated to approximately 100 watts. And from a cooling perspective, it gets very difficult when it goes above that. And so from a cost cooling issue, Intel, IBM, not so much IBM, but the main commodity x86 processor vendors are really limited to 100, 150 watts per socket. And so that's really the driving force. And as you scale down and increase power densities, my utilization, I mean, there's an interesting question of how many cores can I use on the die at one time as we move forward. So there's a lot of things in play that are completely outside of this, but you could understand that if I have these power models, I'm going to create power models for power islands within the chip. If an island has 4 processors, then my control granularity is at that level versus 1 processor. I can do independent DVFS, dynamic voltage and frequency scaling as well, and so I have more features that now have to be in the model because there's more things that I can actuate. So that's what you would see as you would progress down that space. And Intel and AMD are going that way in terms of having processor power islands, independent dynamic voltage and frequency scaling, so forth and so on.
Hi. I was wondering if you're familiar with nonlinear control systems with neural networks and how that would compare at all.
That is outside of my domain of expertise. I'm on the computer architecture side, so I'm really more about the system. I worked with a machine learning guy who helped with the linear regression, the feature selection, and all that process. It was a great learning experience to understand where machine learning broke down and where it was applicable, and understanding what type of understandings you have. But really your point is going to, I used linear regression for this, I used quadratic modeling for that, whether it was multivariate spline or whatever, why not apply neural nets, right? That's kind of where I'm thinking you're going. Is that right?
Yeah, it's for tuning stuff. If you know Bernard Woodrow's work at all,
Yeah.
That would seem applicable here.
Yeah, there's a lot of different techniques. The problem becomes really understanding what the output is. So for our stuff, it's very easy to take these linear models and understand what the feature selection and how it relates back to the actual system. If we started with quadratic models where I can have features interact or give a quadratic factor to a single feature, it becomes much more difficult to tease apart, well, what's significant here and what's not. And so it's really, the interpretation of the model becomes more difficult, and it's a lot more unknowns from that standpoint. I was not comfortable with that.
So you can look at your models and you know what they mean.
Yeah, exactly. So I know that this processor is providing this component of the power. I know that the disk is providing this component of the power from a modeling perspective, right? There's still some hand waving there at the linear level. If I move away and go to these more complicated models, then what ends up happening is these interactions, I might have the disk plus memory in this particular regime of frequency or whatever. Those things contribute X percentage to the model. And that becomes really hard to kind of tease apart and understand. I mean, the other thing that you could do, for instance, is I could use principal component analysis to try to look at the feature selection process. And what that does is it creates basically these vectors which take the features and map them onto that, and the features would be glommed together. And so then how, again, do I interpret, well, this basis vector says that these features, 3 features, are important, and what the heck does that mean? Right? And so this really allows me to understand what the models are and not relying on the machine learning to tell me that these things are important and not having a real discussion of why that is.
Okay, thanks.
Well, one last question.
Being totally unfamiliar with the world of data centers, I was just wondering what level of granularity in time or sampling rate is considered acceptable when one is sampling for all these performance metrics and
Sure.
These knobs that we were talking about, counters and so on and so forth. So what sort of reaction time is considered acceptable?
So that's a very interesting question, because when I start thinking about these collections of hundreds of thousands or millions of machines, whatever, however many, whoever has, right? What ends up happening is the data that I collect now becomes a large amount of data. And how do I save that, and what do I do with it? With the modeling that I've done, I basically provide you instantaneous on the order of a second. So not instantaneous from a processor standpoint, but at a second granularity, you know what the power is. And you can react to that. That doesn't necessarily mean that you're going to log that information at that granularity. What I do know that is public is that Google has a data trace that's available for anyone to download. I think it's about 12,000 machines. The granularity of that data, I believe, is 5-minute intervals. So they aggregate and then probably provide, I think they give you a maximum value in that 5-minute interval plus an aggregate. And what ends up happening in these scenarios when I do any aggregation without distribution information and things like that, I kind of lose information, so that becomes hard. So a lot of people are doing these aggregates because from a storage perspective, there's no way I can deal with that much data, right? I mean, you can just kind of calculate out if I have 500 counters, I'm sampling it at once per second across 100,000 machines, you can do the math and figure out how much data that is and if you want to keep that around, versus aggregates on important metrics at 5-minute granularities, 2-minute whatever, right? I mean, I know Google's trace is at 5 minutes.
So a related question would be, say, for for a given system like Xeon server, what is that delay between that counter moving up by 10 notches to the corresponding amount of power being consumed?
That's a much harder question from the standpoint that empirically for these very simple systems that we were using, we saw that from the point when you hit a threshold, made a change, to it actually reacting to that change could take up to 10 seconds. And the reason for that is there's capacitance, inductance, all these things in the power supply that from the wall perspective masks those change, right? I have capacitance near the processor to absorb these fluctuations, and there's more and more capacitance as I get closer and closer to the wall. The other thing that makes this a little bit complicated is there's power factor correction. So I want that system to look as resistive as possible, and so there's a whole bunch of things that go on to do that power factor correction. So it's one of these interesting things where I was surprised that it would take 10 seconds to see when I changed the frequency down that it would then demonstrate that change at the wall. And so, as a control theorist, you could go in and do some other interesting things, but for me, it was really getting rid of those oscillations. And even then, there are still some, but they're oscillations below the threshold versus oscillations, wild oscillations.
Combine that with the cooling required, then it becomes a lot more slower in response.
So now we're talking about the thermal capacity and right. That's a whole different aspect of.
And it's for continued discussion offline.
Sure.
I think that will conclude it for tonight. Thank you for coming, John. Let's give him a hand.